Good afternoon. Welcome to the BUZZ lecture number 19. Today is going to be the last class about multi-stage stochastic linear programming problems. I think you are already full of the subject, so this is the last one, and then we'll change the subject. Well, what we have seen about the multi-stage stochastic linear programming problems, well, we have seen approaches for dealing with the primal problem and approach to deal with the dual one. For the primal case, primal approach, we saw the equivalent deterministic, and also we saw the nested decomposition. Well, we saw that this is a very naive approach. We can deal only with a certain, just a few number of scenarios, because in this approach, we write our problem as a large LP. So we have problems in memory, in computer, so we cannot solve large problems using this approach. The nested decomposition, we can deal with a larger scenario tree, because we decompose the problem at every node of the scenario tree. So this is more efficient. And we saw also dual approach. One was the dual decomposition. We saw also the augmented Lagrangian for this case. Augmented Lagrangian plus Jacob method. Okay, the difference here is we modulate the non-anticipativity constraints as a set of constraints, this linear constraints, this type. And then when we relax this constraint in our problem, we end up also with a structure that we can decompose and solve smaller subproblems. In this case, smaller subproblems are related to the problem using one scenario, but for the entire time horizon, from the first stage up to the last one. So this one drawback of this decomposition is that the dual variable has a large dimensional, the number, large dimensional variable, the dual one here. So we have a convergence is slow. Have perhaps using another kind of method, not the cut-and-paste method, but a regularized decomposition could be faster. But well, we have a problem with dimension here. It's the same problem here, but here, well, because we are using an augmented Lagrangian, we are regularizing our problem, it's natural that we are going to perform less iterations to converge. However, each iteration is more expensive in this case, because the subproblems are not decomposable. So we need to use some tricks, and you apply the Jacob method to approximate the subproblems and then solve our dual problem. In any case, we can recover a primal solution using just a convex combination of using Lagrangian multipliers of the subproblems. So it's easy to recover primal solutions. So that's not a big deal. But in every approach we have studied, we are assuming that it's given a scenario tree, and we solve our problem based on the scenario tree. And as we have been seeing in the mini course, scenario generation, well, solving the problem with only one tree, scenario tree, is not enough. Ideally, we should solve many times for different samples, and then we can have some estimators of the dual, of the optimal value, and also optimal solutions. Well, today we are going to see a method. It's also in this class, it's primal. However, it combines sampling. It's useful when the scenario tree is very large. The larger is the tree, the better is the solution that you can get, the estimation. However, if you think of a very large scenario tree using nested decomposition, you have many nodes. Let's think. We have to solve one LP for each one of the nodes. So if the large is if the tree is very large, we have to solve many linear problems for every iteration. Remember that in the nested decomposition we have a forward pass. We are going to solve the LPs in this direction, then a backward pass that we are going to construct cut-plane models for the recurse function. Well, imagine if you have many nodes, it's going to be very difficult to solve your multi-stage stochastic program with a large scenario tree. And this disadvantage also happens in every one of those methods, many here. But every one of those methods you have problems. Well, of course, if you have many nodes, it means that you have many scenarios. If you have many scenarios, this decomposition is also expensive, and as well the last one. Well, so today we are going to consider a very large scenario tree. We are going to try to solve the problem for a fixed tree. However, we are going to use sampling in this tree. It's like for a given iteration, we are not going to do a forward pass passing through all the nodes, but some of the nodes. Well, if you are using sampling, well, the idea is, well, if the large is very large, if the tree is very large, sorry, instead of passing through all the nodes, you get just a few of them. You make a forward pass, then you come backwards, because the method is based on the nested decomposition. And it turns that every iteration is much cheaper than the nested decomposition. However, we are using sampling. You can have some errors, you have some difficulties that we are going to study today. Well, and for dealing this is not a very general method, because we need some assumptions on a stochastic process. The assumption is stage-wise independence. Well, so let's come back with our notation. So we are interested in solving a linear, multi-stage stochastic linear program. Random vector can be, as usual, the cost C, this matrix, the recurse matrix A, and the demand vector B. We are already familiar with the dynamic programming equations. And I call your attention here for this notation, because here it means that we are considering all the history. So if you get what's important there is we are going to have here a problem for this node. Plus a recurse function that depends on this stage, this variable, but also the history. So this history means, well, we are here. Here we have our constraints. Well, we are going to have a recurse function, different one in this node, and also for each one of the nodes, we have a different recurse function. Today we are going to consider, so this is the case of a time stage, the time-independent stochastic process. It means that what's going to happen in the future depends where we are today. So if you are here, you have different futures. Another point. But if we assume stage-wise independent process, it means that the future for each one of the nodes is the same. It's like so I can let me draw another tree here. I can say, for example, okay, for this for the future of this node, we have blue, green, orange, and here, for example, I have white, have yellow, here yellow, so it doesn't matter which node we are at this stage, the future is the same. Okay? This stochastic process. Well, of course, the decision X we are going to make at this node will depend on the decision you made here. But the uncertainty, no, the uncertainty is independent. This is what the scenario that will be revealed that in this node is the same here. The uncertainty are the same. Well, another way to write this tree is like that. And here we have yellow and white. No, this is an alternative way to write this scenario tree. So it's the same representation. Well, it's the same tree, but another different representation. What's important here? Well, we saw when we have when the stochastic process depends on the time, we have a recurse function for every node here. But here the future is the same. So for all those nodes, we have only one recurse function. So for every node, our recurse function is the same. xt. And here will not depend on the history. Because, well, it doesn't matter if you are this node or that one, the future is the same. So we just represent in this form what is written down here. Okay? So this is an assumption we are making. So not all the stochastic process satisfy this assumption, of course. But there are significant classes of stochastic programs satisfying this. And also, when it doesn't satisfy, we can also make a trick to convert a stochastic program with time-dependent process in a stage-wise independent process, depending on the class. I will give you an example. Okay, this is just the tree I draw, more or less the same idea. Well, here is an example. Sometimes it's possible to change the problem's formulation in order to obtain an equivalent problem, but with a stage-wise stochastic process. Well, okay, we'll write down this problem again. This is our problem at stage T. So let's consider this subproblem and let's take a look at those assumptions. So we are supposing here that the problem has data except this vector B is stage-wise independent. So it means that if we have uncertainties related to matrix B, to matrix A, or vector C, this uncertainty doesn't depend on the past, on the time, okay? But this one depends on the time. So we don't have a stage-wise independence assumption in this case, because of this vector B. Now, let's make an assumption that the stochastic process of this vector B follows an autoregressive process, which is the value we have today depends linearly on the value we have yesterday plus a random value here, epsilon t. Okay. Now in this case, this is random because epsilon is random. But when we are forecasting realizations for the time t, we know what happened in the past. So with this assumption, well, we can make a trick and transform this subproblem in a stage-wise independent one. So how we can do that? The trick is the following. We can is this function. This is a function q depending on t, xt minus 1, the history. We can write this problem like min I will pass vector bt here. Then I will write what comes in this part, in this argument. This equation. I use this formula. Instead of writing bt, I will write this one. bt. I can write that equation in this sense. Just like that, no problem. the random variable here, sorry, the variable, decision variable, is xt non-negative, and I will consider b as a variable too. But I don't know, it doesn't need to be non-negative, it can be free. The fact here, what becomes random? Vector C, we know that if it's random, it's stage-wise independent. The same for B and matrix A. And now, we are assuming that this random identity, this random variable, is independent too. Independent. So, all the random variables here are independent in this case, but we have this additional variable. This problem, you can write it as Q. To formulate this problem, we need this value, what happened in the past. So you pass to it, to this LP, what we were used, plus this past. What is random here is this QC T that doesn't depend on the past. QC T in this case will be, I don't know, C, A, B, and epsilon. Now this new random, this new stochastic process is stage-wise independent. And well, if you give different names here, we have a multi-stage stochastic program under the assumption of a stage-wise independent stochastic process. So it's just a small trick. What comes here? Well, now this new random vector, and that's it. So if you stochastic process in case B, you could have more terms here depending on the past. You could use the same trick. You are going to enlarge the decision variable. Only that, but it's possible to make this trick. And this is, well, this trick is very useful. For example, here in Brazil, people use this for in the planning power system planning problem. Because if you think of many here in Brazil that we depend to generate electricity, you depend on the level of reservoirs in the hydro plants, and the amount of water arriving today depends on the rain that happened last month, for example. And you have a process, not so simple as this, but you have a process, stochastic process satisfying this assumption. So you can do the same trick and end up with a stage-wise independent problem. Well, I just, here's what I wrote on the blackboard. Nothing new, just a simple trick. So, as you can see, this is stage-wise independent. Of course, we can apply the nested decomposition to solve our multi-stage stochastic problem based on this tree. Okay, we have, if you compare with this one stage, this is time dependent. You have many nodes. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here we have 1, 4, 6. You have less nodes, much less nodes here. And if you increase this tree, increasing the time horizon or the number of children with each node, you are going to see that the difference with the number of nodes between these two trees will the difference will be bigger. But we can apply the Bender's decomposition to solve a stochastic program based on these three. No problem. And well, the idea is the same. We approximate the recourse function by a cut-plane model. This is not a novelty because we already saw. So those are the cut-plane, the cuts approximating the recourse function. When we approximate the first stage, we have a lower bound for the optimum value. Based on the Lagrange multipliers related to those constraints, we can compute the coefficients for the cuts, and approximating the function, and this is our cut-plane model, just the maximum of those cuts. By the way, in the exercise list, you have to compute cuts. Well, the same idea here, just to change the index, you can compute those cuts. Well, I think I wrote here, just to recall, this is the nested decomposition applied to this problem. So the first step, since we don't have any cut, the first step you approximate this function just by a lower bound. For example, we could consider R, you put a variable R where it's this here. So when you go for the first time in a forward step, you can just ignore this variable here and just making decisions without seeing the future. Myope decisions that, of course, are not good. So you go in a forward step, solving each one of those LPs for all the nodes. So you have to visit all the nodes of the tree. You go in a forward visiting. When you arrive at the end, we have a upper bound for a given iteration, upper bound of on the optimum value. Solving again, when you solve those LPs, we have Lagrange multipliers. We can construct a cut, approximating the recourse function in each node. Note that to construct this cut here, we have to go for the forward pass, accessing this scenario, this branch of the tree. And then we are able to compute this cut. In this tree, if we make a sampling, for example, on a forward pass, I just want to take this scenario. You go. When you arrive here, we don't have any guarantee that the value will be an upper bound. When you come backwards, well, we can compute cuts here, but we cannot compute cuts for the other nodes. So in this way, making sampling, just take one path to go in the forward pass is not a good strategy in this case. So you have to visit every node. What was saying? When you come back, well, so here we solve again the nodes, and you compute a cut for this node, the root node. And the process repeats. You go, then you come back, plus cuts, and so on until we approximate very well the recourse function. And we saw that the method, the nested decomposition, stops after finitely many iterations and finds the optimum of a scenario tree-based problem. So we always know that in the forward pass, we compute an upper bound, backward pass a lower bound, and we stop when those bounds are small enough. Well, in this case, we are not taking into account the assumption of stage-wise independence. We are visiting all the nodes, no assumption. So this methodology works in a more general context of more general setting of stochastic process. So let's take advantage of this assumption. What happens? Well, we can simplify this step 1, and here will be a bit obscure, but we can, we are going to discuss this part, stopping test. But the main point is step 1 is going to be simplified. So it's like the method we are going to see, explore our assumption, the forward pass. When you come backward, you do exactly what we do for the nested decomposition, okay? So let's focus on this part here. How can we take advantage of our assumption? Well, the first important thing is, under the assumption of stage-wise independence, stochastic process, we have only one recursive function for each stage. Why this is important? Imagine that example I told you. We select a scenario in the forward pass, and that's it, then you come backward. But I mentioned, well, we can compute a cut for this node, but we're not able to compute a cut for the other nodes, for the other recursive functions. But here's only one recursive function. So if you take, for example, this path in a forward pass. We come back here. Since we have a decision x here, we can solve those two, the LPs related to the two nodes, compute a cut for the function. But our function is only one. So if you take only one scenario, you can still update, improve the cutting plane approximation of this function, because you only have one. And then if you only have one, let's think of the beginning of the process, the iterative process. Nested decomposition, you take all the scenarios. But the first iteration, we make myope decisions because we just ignore the future. You have no representation of the cutting plane, no cuts representing the recursive function. So it's like you close your eyes and make a decision here. And then we are going to correct those decisions in the backward pass. Of course, well, we are going to make a lot of useless decisions at the first pass. Because you don't know anything about the future, you make a wrong decision here, there, and so on. And you solve many LPs, you came back, it was a difficult, a time-consuming iteration with wrong decisions. And you know that's wrong because it's the beginning of the iterative process. Now imagine here, beginning of the iterative process, I don't know the future, no cuts. I just take one scenario, for example, and I go easily, faster, just one scenario, and I come back and backward pass, adding cuts to this recursive function. Again, go with one scenario, a different one. I can just draw it randomly, and come back adding cuts. So every iteration will be much cheaper because you are considering only one scenario to go. And well, you can consider as many scenarios you wish in the forward path. Of course, if you consider less scenarios, you go faster, you come faster, but then backward is backward, there's a difference in the complexity, the computational effort we are making the backward pass. But I will leave this for later, because I want to show the algorithm. Well, let me see here. There exists only one recursive function, well, thanks to our assumption. Any chosen scenario in the tree touches this recursive function, as I explained it, because we have only one recursive function representing the future cost. Even if you choose only one scenario in the forward pass, the backward pass visits all the nodes. That's true. Suppose here, you take this scenario to go. So when we want to add a cut here, we have to visit the children nodes of this one. You have two. And then you compute a cut approximating this function. Then you are in the root node. To compute a cut, you have to visit all the children nodes. So at the end, you visited all the nodes of the tree, the backward pass. It's not the case here. If you take this scenario to go, and then we come adding cuts, well, we don't visit all the nodes. For example, we don't visit those nodes here. Okay, this is what I have just said. Well, this idea of selecting a sample of scenarios in the tree to make the forward pass is the main idea behind the stochastic dual dynamic program, which is called SDDP. And this method, made in Brazil by Pereira and Pinto in beginning of the 90s, if I'm not mistaken. This method made it possible to deal with a much larger scenario tree, multi-stage scenario tree. So this is a very, very powerful tool for dealing with multi-stage stochastic linear programs. Now there are extension, people are using this approach for dealing with non-linear programs too. It's a very, very important tool. So it started here, or was proposed here in Brazil. So the electrical system uses this method, and then this was used in other countries. So many people nowadays using this method and making research on this algorithm. And it works as follows. Well, let's make some assumptions here. So the main assumption is this: stage-wise independence. Then that we have the recurse function are finite valued. So we are assuming, for example, we are assuming relatively complete recurse. Our scenario tree has a finite number of scenarios that I put in this set. Okay, I call this set all the scenarios of the tree, representing the considered tree. In the forward pass, at each iteration of the algorithm, so you think like the nested decomposition with sampling in the forward pass. At each iteration, we are going to select some scenarios of the tree to make the forward pass. Not all of them, just some. So when we arrive at the end with a smaller sample, this is a subset of this one, okay, just some scenarios. So when you arrive at the end, solving all those LPs, we can estimate an upper bound. If you compute the expectation of all the costs related to the scenarios we visited here, we can compute just estimating an upper bound. We cannot ensure that this value is indeed a upper bound. Okay, just an approximation. Then a backward pass, it's like in the nested decomposition by considering only the points x that we constructed during the forward pass. So for example, if I take this scenario, so here I defined a x1k at iteration k. Here I defined x2k, x3k. If I take another scenario, so here is the same decision, but here I have another one. I call it tilde, k, 2. So when we are going to construct the backward pass, we are going to solve those LPs when we send this x tilde to those nodes. We solve the LPs and we construct a cut. Here we have another point, because we passed through this node. We can send this x also to the future, compute a cut, and we'll take the maximum of the cuts. We have approximation for this. But see, we haven't computed any point at this node at this iteration. So we don't need to send any, we don't have anything here to send to the future to construct some nodes. It's clear, well, it happens that the number of LEPs in the backward pass depends on the number of scenarios. It's a proportion. It's like a sum, but not here. If you consider here, here's the product. If you have consider all the scenarios, the number of nodes you are going to visit from the backward pass, this is it's a product of the nodes, the children nodes. The product of children nodes. Here is a sum of children nodes. So this is much cheaper. It's a sum. So you are going to visit less, solve less LEPs. Although you are visiting all the scenarios, but we are solving less LEPs. When you come back, backward pass, at the node, the root node, you have to solve this LEP as in the nested decomposition. And this is going to be a lower bound. This, the optimum value is a lower bound for the optimum value. Why? Because our recurse function, we know this convex. At every iteration, we are approximating this function from below. So if you visit this point here, probably the recurse function here will be better. But well, you didn't visit, so the recurse function can be a bit can be poorer. But although is approximation from below. So when you solve the node, root node, we have a lower bound. So what we know? Backward pass still ensures a lower bound for the optimum value. However, forward pass, no. So how can we stop the method? We don't have now a optimality gap. We just know that the lower bound is indeed a lower bound, but that estimate for the upper bound, well, we don't know. Sometimes this estimate, when you come here in the forward pass, this estimate can be under the lower bound. We never know. This can happen. Well, and there are research in this area how to stop the SDDP algorithm, ensuring that you are you have gotten an approximated solution for your problem. Well, there are research on that. We are not going to discuss this. I would say that one way of stopping the algorithm is fix the number of iterations. I don't know, you make 300 pass, for example, forward pass. It's some way. You stop, and what you have, this is what it is, and you keep in mind this approximation. The lower bound is approximation for the optimum value, and the solution you are going to have is an approximate solution for the optimal policy. Only that. There is this method here, this test you can also use, but you don't have. I think we don't have guarantees that this will be satisfied, because it's like well, the upper bound. Let me see. This is upper bound here. So we know that those two trees are equivalent. Let's take a look at this one. So for example, in a forward pass, I select this scenario, this one to go. So in total, we have 6 scenarios, and the forward pass, we just consider 2. So we are going to have here this approximation for the upper bound that is based only on that sample of 2 scenarios we took at this iteration, in this case, of the costs at each stage. Well, this is indeed a stochastic process, a random variable. This is a random variable because you chose this randomly, the scenarios randomly. And we can ensure, well, you can use some confidence intervals, well, and say that this belongs to a certain, no, in fact, we can think that an upper bound, if you consider all the scenarios, belongs to an interval set. For example, what did I write here? This is sample variance. In our case, 2 scenarios. So this we can say that, well, an upper bound is with probability, in this case, 95% inside this interval, this confidence interval. Well, it's like we have a lower bound, we have a upper bound, we have an interval confidence for this upper bound. Okay, those streams. And one alternative to stop is when the lower bound, when this difference here, this upper, and this, when this distance is small enough, then you can say that, well, with a probability of 95%, the difference between the upper bound and lower bound is less than this given tolerance. Okay, this is our way, but we don't have. We cannot ensure. I think the size of this interval, the length of this interval, depends on this sample variance, and the sample variance depends on your problem. So if you have, if you are dealing with some data with high variance, a large variance, it's natural that this interval will be larger. And you can, perhaps if you use this test, we are going to stop sooner. Because, well, this is, no, if it's larger, no, indeed, we are going to stop later. But everything depends on the variance. Well, I think one of the most, people are stopping the SDP if maximum number of iteration, right, Philippe? But you have more experience than me on this matter.
Yeah, they have this stopping criteria, but also they use some kind of lower bound stopization.
I think I have written this on another slide. So what Philippe said is the following. We can stop also, well, you fix on the maximum number of iteration, and we stop when the lower bound, because at every iteration you are going to increase your lower bound, because we are adding more cuts. So when you see that we are not moving so much, so you go forward, you come backward, and you are more or less the same place, you can think, well, this is, perhaps I'm near to the optimum, I will stop here. That's a way of stopping. But all of these are heuristics. Okay. Okay, a very simple version of STDP algorithm is the following. So as I told you, we are based on the nested decomposition with some changes. The first change, the most important change, is the forward pass. Here we're just going to randomly draw some scenarios to make the forward pass. We estimate an upper bound, can be useful or cannot be useful, depends on your stopping test. The backward pass is essentially the same, however, we are going to solve this LP for all the x's related to the scenarios we made the forward pass. You are going to update the cutting plane model, and we stop according to some criteria, some heuristic. Okay, that's it. It's simple. The idea behind is simple, and this is very powerful. In practice, you see that, well, you can solve problems that you could not imagine to solve if using other approaches, because of the size of the tree. Some remarks here. You can vary the number of scenarios in the forward pass. So, according to a good friend of mine, Vitor de Matos, he uses at the first iterations just a few scenarios to make the forward pass until you have some more or less good approximation of the recurse function, and so that you may increase the number of scenarios to make the forward pass. So in this way, you accelerate the algorithm. The first iterations are going to be cheaper because you are considering less scenarios. Of course, if you consider more scenarios, more cuts, you have a better approximation for the recurse function. It's a trade-off. For convergence analysis, we assume that every scenario is with probability 1 chosen infinitely many times by the forward pass if the algorithm loops forever. I think this is an important assumption for the convergence analysis. It means if you run your algorithm forever, the assumption is you visit any scenario. Let's fix this scenario. You are going to visit these scenarios infinitely many times. If you run your algorithm forever, it means you are going to visit all the scenarios, and not only once, but infinitely many times. And I think this is a result of a Borel-Cantelli theorem if you just make sampling. If you choose randomly scenarios, you can ensure this. So there is a lemma that ensures this result. If you choose randomly, and if you run your algorithm forever, with high probability 1, with probability 1, we are going to visit every scenario infinitely many times, with probability 1. For example, for instance, the convergence analysis of SDP is based on with probability 1, because we have to assume that with probability 1, we are going to visit all the scenarios. The algorithm may stop when the lower bound stabilizes. That's what Felipe said. You fix a minimum number of iterations, for example, and after that minimum of iteration, you're going to check. You are not change this bound so much, well, you may stop. So an interesting property of the SDP method is that the computational complexity of one run of the involved backward and the forward step procedures is proportional to the sum of the sample data. This is what I explained, and not the multiplication of the children nodes. So this is cheaper. Here we just consider so far in the course you are considering just a neutral risk version. But from next week on, so we are going to study, so Juan Pablo is going to teach some risk measures. So we are going to deal with more involving expressions, not only the expectation for the recurse function. Well, about the convergence analysis. So in fact, the convergence analysis of SDP was made some years after the paper proposing the methodology for different researchers. And the idea is the following. Why this method works? We are in the linear case. Let's assume that this set is bounded for every stage, for every scenario. You have bounded sets. You have a scenario tree with finitely many scenarios. And we are assuming relatively complete recurse. It means that this function is finite valued for every x we choose. Let's make this assumption. Well, if you draw scenarios randomly, we are going to visit each one of the scenarios infinitely many times if you run the algorithm forever. It's natural, and at every stage we have only one recurse function, which is polyhedral, convex polyhedral. And at every iteration we are going to add more cuts. So it's natural that eventually our cut approximation will coincide with the true recurse function if we make enough passes, forward and backward passes. So that's the idea behind the convergence analysis. And well, because this recurse function has, you can approximate it using finitely many cuts. So every iteration you construct a new cut, eventually you are going to converge. So this is the idea behind the convergence analysis. And if you check the proof of this proposition in this paper, we are going to see that it's exactly what I'm saying here. Well, I read that paper, so this is why I'm explaining. And the ideas there is just this, based on that. It's not difficult. You have to argument all your assumptions, and then you get this convergence, which says, with probability 1, after a sufficiently large number of backward and forward steps, the forward step procedure defines an optimal policy for the problem. And you have that the lower bound will be the optimum value of the problem based on scenario 3. That's the result we have for this case. There are other methods based after SDDP. People start to make research on this algorithm and try to improve. For example, there are methods that doesn't randomly draw scenarios, but nodes. For example, in this case, we would draw this node, but not in the future. And well, when you solve this node, we can also get some sort of improvement on the cut plane model for the recurse function. And well, it seems that you have more information, have a better approximation. People say that this strategy of selecting randomly choosing randomly nodes instead of scenarios is better when you have a tree with many children nodes. And this idea of choosing scenarios is better when you have a long horizon, but a less number of children nodes. So there are different strategies to try to improve the SDDP. But SDDP, I think, it's the main algorithm. It's for sure the main algorithm of this class of combining sampling and optimization. There is another method which does the following. It's called CUPS, cut-planing and partial sampling. At every iteration, the forward path, just select one scenario to go, and it doesn't have backward path. It's the following. You choose, for example, this scenario. You come here, solve this LP. When you solve this LP, you get for free the cuts. You can compute the cuts because you have for free the Lagrange multipliers. You can compute a cut. And when you solve this just once, you can compute a cut here. And then you move forward, get this node, solve, compute a cut here, approximation. It's a poor approximation, but you can compute. And then it doesn't have a backward path. It comes here again and select, for example, randomly another scenario and does the following. And it has also a convergence analysis, always with probability 1. Because, well, depends on if you are visiting all the scenarios or not, or many times. But, well, the main algorithm is this SDDP. Do we have questions about this method? Some comments? Philippe, do you have comments? You are an expert. No? Hmm?
No, I think this is all
Yeah. Okay. Well, so I finished this. I don't finish the class now, but we stop with this with the material, new material, and I would like to discuss with you the exercise list. So if you have some questions about the exercise list, we can discuss a bit. I will perhaps would like to give you one or two devices, and well, you are supposed to provide this list, the exercise, on June 2nd, right? June 2nd. From next week on, well, no, next week, Juan Pablo, you give some classes, and at the end of the course, I will come back to study some more efficient optimization methods for the two-stage stochastic program, two-stage setting. Okay, so I think for multi-stage, that's all. I'm not sure if Juan Pablo will talk about it, but I think in terms of algorithms, I think this is all for this course. And then we are going to come back at the end of the course with the two-stage, but more efficient methods, and much more efficient. Let me open here the exercise list. So the other students who are following us by YouTube, if you have questions, just write me. I will answer you. Well, first of all, do you have questions about the list? You can ask in Portuguese if you want. In Spanish, I don't think I can understand well. No questions? Okay. Okay, so the question was, can we change the code, make some change in this last part of the code? Here, you mean? Yeah, yes, no. Here you can change. So if you think you can improve something here, or if you want to make another tests, so you have freedom to change this part of the code. For example, here there is something that Felipe pointed out. In the list of exercise, we are not asking to perform out-of-sampling simulation with the solution obtained by the equivalent deterministic method. But in this case here, if you use this algorithm, at the end, we are going to make some simulation. Now, if you want to make simulation, it's okay, but it's not. We are not asking this in the list. Well, so here you can change. However, I would like you to keep the input structure. So I would like to pass, for example, the number of scenarios and the algorithm we are going to use. Because when you send us your codes, we are going to test. And well, I would like to say, I would like to verify if your code works with n equal to 50 scenarios and algorithm 2, for example. And I will see. If your algorithm crashes, well, I will open, I will see what's going on, what's the mistake, and we are going to try to help you. But I would like to keep the input structure. The output, well, I would like to have the optimum value, CPU time. I would like to have a number of iterations when it's applicable. So if you want to return some information or other information, well, it's up to you. No problem. Let me see if there is something. Okay, no, not here. This is important because, well, this data PBM generates the data of our test problem. So we are going to code your programs At the end of the course, we are going to make a evaluation, an exam, and the exam will be based on your code. So we are going to give another problem, and you are going to use your codes to run that problem, to solve a given problem. And what we are going to give? Another function here for you, for example. And you come here, change for the new function, and when you run your code, it should work. So this is what we expect. So try to make your implementation very general and think of, we are going to give you another problem with different assumptions, and your code should solve it. Philippe.
I tried to let's say the BBCut function that
Mm.
provide first statement decision,
Mm-hmm.
then give output.
You are going to speak, I'm going to search here the BBCut.
And then it output the optimality cut or the feasibility cut.
Okay, it returns optimality or feasibility cut.
So I didn't find first state feasible.
Okay, okay.
That outputs
Let's.
gets the feasibility to the same.
I'm going to discuss this. Okay. This is the function Philippe mentioned, the BBCut. Well, the question was, what Philippe mentioned was the following. He tried for many scenarios to compute here the optimality cuts and the feasibility cuts. I don't know where I wrote this in this part. Containing the cuts coefficients. Okay. Depends on the ind, right? And all the scenarios you tested are feasible in the second stage. This is also happened with Adriano. I'm not sure, but okay, I'm almost sure that this problem has relative complete recourse. So if you don't find any infeasible subproblem, I think it's normal, because this is a nice problem. Okay. However, try to change parameters or something to test your implementation of feasibility cuts. Because in the exam, we can provide you another problem which doesn't satisfy the relative complete recourse assumption. And then we are going to, your code must be ready to compute feasibility cuts. Okay.
Another question is that I think that my implementation of the Shapiro method is much more slower than the equivalent, the deterministic equivalent. And I think that this is due to the BBCut function that we are calling, and this is taking too much time to be evaluated.
Okay, just let me repeat your question too here. So the comment was the implementation of the second question was L-shaped method is lower than the equivalent deterministic. And you think that because of the BBCut script is taking much time.
Yes.
Hmm.
And one way to handle this is trying to make some tricks like a warm start initialization.
Okay, you can warm start initialization here, make some tricks to try to improve this BBCut routine.
I didn't find the way to do this with the MATLAB function info. I don't think that they have this kind of functionality.
Okay, yeah, the MATLAB, the limprog doesn't have this functionality of, I think, warm start. I think it doesn't have. If you want to make warm start here, you have to make it on your own. You have to code it. For example, how you code it? You have to solve n LPs. For example, the first iteration. Save those dual problems, dual solutions. The second iteration, when you call this function again, you have some dual feasible solutions that you can apply. to warm start your problem. But pay attention, this works depending on the assumption of your LP. It doesn't work for all the case. In our problem, the implementation we asked you to do is considering everything stochastic. The stochasticity can be in Q, T, W, and that's it, and age. If you paid attention when you were dealing with this list, you realized that in the problem we gave to you, only age is random. When only age is random, if you consider the dual problem here, you see that the dual feasible set is the same for every scenario. And then you can do warm start. However, if Q depends on uncertainty, you can still do warm start, but it's more sophisticated. It's not so that simple. Okay? But you mentioned the equivalent deterministic is faster than the L-shaped. And the idea, that's true if you are considering just few scenarios. Because this is a good test. Run the two scripts, the equivalent deterministic and the L-shaped method, and vary the number of scenarios. You are going to see that for a small scenario, a few scenarios, the equivalent deterministic is much faster. And when you increase the number of scenarios, then the L-shaped starts to become faster, and the comparison. And well, if the number of scenarios is large enough, you cannot solve using the equivalent deterministic, but you still can solve using the L-shaped. So that's the advantage of L-shaped. Okay? Well, I didn't test. I don't remember. In fact, I tested. You mean how much time my code takes to solve the equivalent deterministic using 200 scenarios? 2,000 scenarios? Well, I did this test, but I don't know. I think it takes some time. It's not quick. It's not quick. I think it was. But this depends on the computer. Okay? If you have a powerful computer, it's natural that the equivalent deterministic for this number of scenarios will be faster than the L-shaped. My computer, for example, is not so that good. I have just few memory. So if I have issues with memory, the L-shaped will be faster. So you cannot, this will depend on the computer you use. Okay? And perhaps you have some of you, happened with Adriano, tried to run the equivalent deterministic here using 2,000 scenarios, and his computer crashed. You too? Happened too? And what's the main difficulty here? It's because you have to mount a very large matrix, putting all together the scenarios, and this is the problem. You have issues with memory there. So this is why we wrote try. Because it will depend on your computer. You may not be able to solve. Well, my first implementation, I have to say, I tried the 2000 and I couldn't solve. My computer crashed too. But I saw that I was doing something naive when I was mounting. That's the hint I would like to give. So I was doing something naive when I was mounting the matrix. If you pay attention to that matrix you mount here, it's full of zeros. It's a really sparse matrix. So for dealing with sparse matrices in MATLAB, you should use the function sparse. So if you define, well, you are going to have a I don't know, for scenarios. And here, every time you do a loop, you are going to increase your matrix. Perhaps I think a good practicing is to define the size of the matrix outside, and not enlarging it inside a loop. It's better. Define your matrix, the size because you know the size of that matrix. You make a computation, you know the size. So define before, and here we are going to fill up that matrix. So define your matrix, I don't know how you call it, but using the function sparse. Search this in the MATLAB help, that we are going to get some explanations. And when I use sparse to mount the matrix, then I could solve it with 2,000 scenarios. So that's a hint I would like to give. Another thing I would like to mention is this is for all the solvers. Try to make it as general as possible. So, for example, don't assume that the probability is 1 over n. Don't assume that only the vector age is random. So assume that everything is random. Because for the exam, we can give you a very different problem with everything random. The problem cannot have the assumption, may not have the assumption of a relative complete recourse. We may change the probability. We may give you a file with the scenario's probability. So make it general. So as general as possible, because this will help you in the exam. Okay. I also want to give you some advices about the input and output. For example, this BBcut script. So Francisco yesterday mentioned, well, but why should I return with the same input? Okay, I pass the input, update something, and then I come back with everything. But outside of this script, I have in memory all the information I'm passing here. Why I should keep it back? I know for this list, this is not so much not efficient. But we advised you to do like that because in the project you are going to have to make some modifications in the black box, for example, warm starting or on-demand accuracy that we are going to explain. And in this case, when you use more information, smarter black boxes, you need to leave the black box with more information. So I know in this list, this is naive. But please keep this format because it's going to be useful later. Questions about the list? Has someone tried to code this method? This is well, today we saw the first method combining optimization and sampling. This also combines optimization and sampling, but for the two-stage. The idea is different from SDDP, but it's interesting. Someone? You have. Where? K, you mean K? Well, what is important here is to preserve, you make this combination, what's important, you preserve this inequality. You have other ways to preserve the same inequality. You may test it if you wish. So this is one rule. There are more. Okay? So you can test. In this method, it's like, the first iteration, I generate one scenario, call the second stage, construct a cut. Second iteration, I have one scenario generated, I generate one more, and solve this new one. I get an approximation for the previous scenario, I make a construct a cut and update the previous cut using this rule. When you run the code for this method in the L-shaped, you are going to see that this one, it runs at the beginning really fast. But then at the end, you are going to have issues with memory also. So I would like you to have this experience and, well, pointing out what you like in one method, what you like in another one. It's that idea I have already explained. I don't believe that there is a method that's better for all the problems. But depending on the problem, you can choose a nice method for dealing, for solving. So here I think you are going to get to have an idea. Well, you have to test with other problems. But once you have coded the three solvers, you have the structure of the black box. You can code another function to generate your parameters, your data, for another problem, for example, where it is. So if you have a problem that you would like to solve, and I don't know, you are interested, just make it code a new routine here and test your solvers. More questions? Okay, no, great. Footnote. This. No, are you familiar with LaTeX?
Yes, but not with the spectrum.
Okay, at the beginning, you just put there, use a package, something like that, and mstyle, mcode. Just that. You use this, and when because I use this package to write like that. Then there is a comment when you want to put your code, okay, in a part of the text. Then we are going to start there in LaTeX. Begin. There is a command related to this mcode that I don't remember now, but if you search in the help, you are going to find a command here. I don't know which is the command. I forgot. And the same code label. And here, you put your MATLAB code. It's just a Ctrl-C, copy-paste. You get your file in MATLAB, copy and paste here. It becomes beautiful like that.
I misunderstood. I thought that we run our MATLAB code and also it publishes a kind of...
No, it's not. No, it's not. It's not so that it's simpler.
Because our language,
I have this. Okay, no, but it's not the case. But this is not mandatory. Okay, that's just to help us to correct. It's not mandatory. If you are not familiar with LaTeX, you don't want to use it. Okay, just use Microsoft Word, no problem. Just but try to make it easy to read. Well, it's going to be easier for us to correct. More questions? You have time? Okay, guys. So we finish this class now, and I will see you at the end of the course.